manipulator. So d dt of dl dq dot minus dl dq equals qj. When you pull this, and I'm going to write this down without deriving it, but you could refer, if you want to see how this comes, you need to go to Spong. There's a book, I think it's in the reference, chapter 6, I think. So it uses basically, what is it's called? It's called using index notation. It basically derives that, assumes that L formula I wrote down earlier with that Jacobian, and then derives that, expands on that, takes the derivative, and shows that you get something which looks like this: m q q double dot plus c q q dot times q dot plus g times q. I'll put something else here. I'll put g. It's not usually written like this, but this will be helpful later on when we try to derive, equals the net torque. We'll call that u. Okay, it's always of this form. Okay. A lot of control is going to be dependent on this form. Because we have this formula for the equations, you can do control, which will do interesting things. So here in this, let's figure out the dimensions of different things. This is going to be n cross 1. Okay, n cross 1. This whole thing is n cross 1. This is n cross 1. Sometimes it's actually, you can just write it at CQ dot. Let's not write Q dot. It actually is there's a Q dot square term there. If you have heard or seen of the Coriolis force, this is something which depends on velocity squared. That comes there. And then this mass matrix is n cross n. So MQ mass matrix. Okay. The key thing is only a function of Q. It's very important. This is a fact we'll exploit later on. It does not depend on velocity. CQ, Q dot is nonlinear Coriolis centripetal acceleration term. Okay, it depends on both Q depends on Q as well as Q dot. Okay, and then GQG is gravity term, and it depends on gravity and Q. Okay, this is kind of only on Q. So this is something which we'll be exploiting in just a bit. So when we do this in SymPy, you will get basically lots of characters which will be basically the equations, right? And what you want to do is you take that equation and write it in that form: MQ CQ plus GQ equals U. Okay. Okay, so we have this, which will be, the best way to explain this is to probably look at the equations, and then I'll show you how to extract M, C, and G. So we'll derive the equations of motion for a 3-link planar manipulator using Euler-Lagrange equation. Okay, so just like we did this for that single link pendulum, I've done this for a 3-link planar manipulator, which you've seen in the past. I need to define everything associated with the symbolic variables. It'll be angles, velocities, angular acceleration, mass, inertia. We only need one number for inertia because it's only going to move in the z-axis. So only the inertia about the z-axis, the lengths. Okay. Now I'm just following that same recipe: position, velocity, Lagrangian, and equations of motion. So first get the position. So I define the homogeneous matrix H01, H12, from which I can get H02 as H01 times H12, H03. I get the position of the center of mass. So G1, G2, G3, that's halfway of each of those link lengths. I get the X, Y from this G1. G1 will give me X, Y, Z, but I only want X and Y because it's a planar manipulator. To get the velocity, I use the Jacobian. Now, this is another way of writing the Jacobian. I did not do the formula I wrote down in the past. The Jacobian formula had something like R times N, right? This one's just taking the X and this taking the derivative with respect to Q1, Q2, so theta 1, theta 2. So you can do that using a single command in SymPy. It's just Jacobian X d Jacobian Q, which basically will do, write it down here, dxg1 dq. This is actually the partial, my bad. This d is the partial derivative, not the complete derivative. Okay, so this is essentially done by Jacobian, and the format is this. So it takes dx, g1, dq, and so you can do this for each of these things. This is exactly what I wrote down for the simple pendulum, right? I wrote the x position and took the derivative, but this takes the Jacobian, because what I can do then is the velocity is simply this is, okay, maybe I should write this down. This is times. That's the chain rule basically in action, but let me just write this down so you know what's going on. So if you want to find L cosine theta, I think that's what I wrote down earlier. X equals L sine theta. Okay, let's just use X equals L sine theta. One way of getting this is to just do X dot is L cosine theta, theta dot, right? That's one way, and that's what I did. I just theta times theta dot. Just derivative. So here's another way. You could write this as dx d theta, theta dot. You'll give the same answer. So if you write this as dx d theta, so derivative of this with respect to theta is L cosine theta times theta dot. So this is basically the chain rule. Okay, and then this part here is the Jacobian. So that's what I did with it. Okay, so I can do that for velocity of G1, the X direction, Y direction, so on and so forth for all the 4 links. Then I collect it as matrix, a 2 cross. In this case, I just use, I think it's 1 cross 2 in this. Yeah, it's 1 cross 2. It's not 2 cross 1. I, however, can use the dot product to get the scalar. So then what I do is I compute the kinetic energy, which is just half mv square, but I need to take the dot product. The dot product gives me a scalar. Same thing for the rotational counterpart. The angular velocity is going to be of link 2 is going to be omega 1 plus omega 2, and omega 1 plus omega 2 plus omega 3 for link 3. And then the potential energy is, remember that indices start from 0, right? 0, 1. So y1 means the y position of G1, y position of G2, and y position of G3. So mgy1, mgy2, and so on. L is t minus v, so I get that. And then I make it print, don't have to do that. The third piece is derive the equations. So I need to do these things, dl, dq dot, ddt of dlq. I just have a kind of an efficient way where you don't really have to do and do it one at a time. I wrote a code which essentially does all that calculation for you, so you don't really have to bother writing down individually for each of those lines for the anyway. So you get the equations of motion. This will have, remember that this is a loop which runs for 3 joints, so there'll be 3 equations: EOM 0, EOM 1, EOM 2. Okay, this is where let's stop. Intentionally putting that, it'll actually quit there. Let me just print EOM 0. So this is going to be the first equation, second equation, and third equation, right? It comes from here. I just appended it. So I wrote first equation was derived. I was put it in EOM. I took the second one, third one. This thing actually just converts into matrix. It has no much consequence. I just wanted matrix because then I can do more calculations on this. Just put okay. Let's run this. So it's going to quit. It's going to complain after it comes here, but that's not a problem. I just wanted to stop there. Okay, stop. So it's given error, but that's intentional. Okay, so this is what the equations look like. This is let's copy that. Okay, app. Okay. Okay, so this is EOM 2, EOM 1, and EOM 0. Okay, so just 3 links. Okay, now this is, we can use simplify. Let's see if that helps. You do sy.simplify. Two. No, 0, 1, and 2. Okay, now let's run this. Here's the kinetic total. Okay, EOM. Now it's going to do a lot of work because it needs to simplify. It's paused there. Sometimes simplify just stops forever, so it can't simplify. But I think I have hopes that it'll be simpler than what it is over here. Yeah, so this is why you'll appreciate the numerical solution a little bit later. It's because of this. So EOM 0 was that. It printed. EOM 1, it's thinking. Okay. Okay. Error, not a problem. Let's take this. Might have gone too far. Hold on. Okay, so EOM 2, EOM 1, EOM 0 here. Okay, not too bad. This is the original. Without simplify, little better, but still a mess. And remember that this is only because inertia is only one term. There is only 3 links and so on. So, okay, so there's this thing which comes from Euler-Lagrange, but what we want to do essentially now is put it in this form. This form. And I promise you that this form is much, much simpler than that form. Okay, so how do we get it in this form? So what we're going to do is the following. Okay, so if you want to find, so what we've got here is EOM 0, EOM 1, EOM 2. Okay, now we need to extract from this M, C, and G. How do we do that? So the first thing we can do easily, which is kind of straightforward, is if you take this equation and take the Jacobian with respect to Q double dot, then you should obtain M, right? Because Q double dot doesn't appear anywhere else, so it'll all be 0. So to get M, all you need to do is, let's call this EOM. Okay, so then you take the derivative of EOM with respect to theta 1 double dot, derivative of EOM with respect to theta double dot, where theta double dot is theta 1 double dot, theta 2 double dot, theta 3 double dot. So that's super easy, just that. Now let's look at the second one. In order to compute C, we need to somehow eliminate this piece and this piece. This piece is only a function of gravity. So if you put gravity equal to 0, okay, turns out that gravity always shows up in all parts. So this is something you need to know, which is if gravity is put to 0, then that whole thing disappears. It just becomes 0. So what you can do is you can take that EOM and put Q double dot equal to 0 and G equal to 0, and you'll get C. So second piece, to get C, you take EOM, which is a function of Q double dot, Q dot, Q, and G, and put these two equal to 0. Right? Just from this form. That is 0 and 0. And the last piece, if you want to compute G, then what you need to do is you need to put Q double dot equal to 0 and Q dot equal to 0, and you'll actually get G. Or you could take, you could put Q double dot equal to 0, which will give you the sum of C plus G, and then subtract out C, which you already computed. So to finally, third step, to get G, you take the EOM and you put Q double dot equal to 0 and Q dot equal to 0, and keep Q and G as it is, and get G. It'll actually be the negative of this because you have to move it on the other side. I think that's what I did. So if you go back to my code, okay, let's not make it simplify. Okay, so M, I did Jacobian times Jacobian of this to get N1, N2 work. So N1, here what I did is slightly different. I said N equals C plus G. To get C plus G, what I need to do is, let's go back to the equation. So C plus G, if I want to get C plus G, I just put Q double dot equal to 0, and that's what I did. I put all those accelerations to be 0. So alpha 1, alpha 2, alpha 3 acceleration 0. So I got N1, N2, N3. And then to get G1, G2, G3, I essentially put subs omega 1, omega 2, omega. So I put in this term, now that you have the sum C plus G, if you put Q dot equal to 0 in this sum, then you'll get G. That's what I did. There are multiple ways of doing the same thing, essentially. So this is how I get. and then C was N1 minus G1. Okay, so that's one way. I showed you another way in the notes, but either all those methods will give you similar answers, just that you need to notice what is a function of what variable. And now what I'm going to do is, in this mass matrix, it's going to be a 3 cross 3. I'm just going to print M1, M12, M13, and so on. So the 9 elements. It so happens, if you check later on, that M12 will actually be equal to M21. And then C1, C2, C3, those are the 3 rows of C and 3 rows of G. So let's run this now. If that's the kinetic potential energy, I'll talk about it in just a bit. But here is M11, M12, M13, M21, M22, M23, so on and so forth. Okay, it's not that compact, but you could use simplify and that make it easy. So this, I'm just going to copy this because I'll need it in just a bit. So all those things. Now, the last step is, and this is the first time we're doing this, which is a forward simulation. So what we have got from this entire exercise is this formula, right? We have I'm going to skip the function of u. Let's say that there was no control. This is 0. We don't want to put any control. So we can solve for q double dot as minus m inverse c plus g, right? And then if you want to simulate the system, you need to do what is known as integration. So q dot is going to be integral c plus g, and then q, let's call this omega, and then q is integral omega. This can be dt, and then dt. So we need to integrate this accelerate. This is the angular acceleration to get the angular velocity, which is omega, and then take this integrate again. So think of angular acceleration has to be integrated twice to get the position, right? And once you get the position, we can simulate the system. So once we get q, once we obtain q, we can do an animation, right? We have seen how to do animations in the past. It's just a matter of figuring out the position of the joints. So q is theta 1, theta 2, theta 3. Now this thing is done by an integrator. The integrator I'm going to use called ODE int. It's I think it's a Runge. You don't need to know too much about this. It's a Runge-Kutta integrator, but the other ones you might have heard of are Euler's method. And then this is actually Runge-Kutta adaptive. Runge-Kutta fixed and order 4. Okay, actually MuJoCo uses these. If you look at MuJoCo documentation, it actually uses one of, you could use one of this. This is more accurate. Okay, so don't worry too much about the thing. If you want to go and check this out, just check how do you integrate equations. How do you use, just search for Euler's method and Runge-Kutta, but we really don't need to know how it is done. So what I've done next is taken those equations and integrated them. So let me drop that code. Okay, so this code is, I hope, not too long. Okay, it's about 200 lines of code, but what I need to do is take these equations and pass it to the integrator. So a chunk of this code is actually taking these equations and copy pasting inside this code. So you will see those equations here, M11, M12. So this is basically the right-hand side, things what you want to integrate. It's going to sit here, the mass matrix, the Coriolis term, gravity term. I've called A as the mass matrix here, and B as the sum of the gravity and Coriolis term. And then I need to take A inverse, right? I wrote it down, times B. This is the same as this thing here, M inverse C plus G. So let me put that here. This is the same as inverse M times C plus G with a negative sign. The negative sign actually appears here, negative. Okay, so I get angular acceleration, and then I need to provide angular accelerations and omega, which is the velocity. So there are six variables which need to be integrated. Integrating this one gives me θ1, integrating this gives me omega1 for the next time step, and so on. So this is basically taking state at the current time step right now and giving me what happens after a small change dt. That is taken care by ODE int, which is, I think it's down here. Okay, so this is the main code. Everything else is functions. So here is, I need to integrate for 10 seconds. I started with 0 position, 0 velocity. So all angles are 0, all velocity is 0. I pass all parameters which I define. And then ODE int, this is just a function which I need to call. It's actually in a package, I think SciPy. RHS is everything on the right-hand side, the equations I derive, the initial value, the time over which I want to integrate, and all the parameters. Okay, then I do an additional step. I get the kinetic potential energy and total energy, which is sum of kinetic potential. And this is actually a good way of checking your equations. If a system like a pendulum shows that the total energy is decreasing or increasing, that means you have a problem, right? Because when you don't have external forces, no damping, or no power, or no torques, the energy should remain constant. So that's a good check. So total energy should be constant. And then I do an animation. So animation is first, then I do the plots, and then I think I do the energy. So let's run this. So this will show chaotic behavior like you've done in the past with MuJoCo. 2-link is enough to get a chaotic behavior, but here 3-link will be more chaotic than a 2-link. So the black dot shows the center of mass. Yeah, so I stop at 10 seconds. This is the position, angle, and this is the energy. The black line is the total energy. It's constant, which means my equations are fine.